Last time we started section 4.3, and it's called Riemann sums and definite integrals. And we'd gone through just like this massive page of notes. It was just notes. And I just said if you didn't even have them printed out, please don't write them all out, right? But let me just remind you where we were when we looked at this. We defined something called a Riemann sum. And a Riemann sum is taking these shapes and trying to use evaluation techniques of letting there be infinitely many rectangles and finding their area to calculate the sum under a curve of the area. We talked about the fact that we can find it exactly if we let those if we take the limit as those rectangles become infinitely narrow. And if we do that, it actually becomes what's called a definite integral. And that notation is one that we saw back in 4.1 with the exception of the a and the b at the top, right? We just had the other pieces of it. And then we talked about the continuity. It actually means that we're going to have something that's integrable. And integrable means that you can actually take an antiderivative. That's what that means. You can find these areas. And the fact that it's continuous means that automatically. And then we said you can actually find the area exactly using calculus techniques if you find the antiderivative between A and B. And we haven't done it yet, but that's what we talked about. And now we're actually on an example. So are you guys ready to take a look at some examples? So there's several things in these last few sections we're going to do, in particular 4.3 and 4.4, that are ways of evaluating these different functions. So there is a picture drawn on page 273 of your book, and I'll just sketch it into here. Sometimes it's not always easy to copy-paste images from your book into a document. And so if you were to look at your book, this particular image looks something like this. Okay, so we have the first quadrant, and we have a shape that looks like this. And the function it gives you is x squared. Okay? And all this is asking you to do is to set up, actually, a little bit more, it actually does this as well. Okay, it actually just says it wants you to set up the notation. So it wants you to take the notation that it presented back here, this definite integral notation, and it wants you to set it up for the function that it defined. Okay, so what this is telling you is that the a and the b are the beginning and the end point of the interval. So what are the a and the b on this problem? It's shaded in too. I'm sorry, mine's not shaded yet. Yours is, your book is. It actually shades it in like this. Okay, there we go. So what is the lower value, the farthest left-hand point, x value, that we seem to have the shading beginning at? 0. It's 0. And where does the shading stop at? 2. It stops at 2. So this is 0 to 2. And then over here, what you see next is the actual function's equation, right? The expression that's on the right-hand side. So that's x squared here. And then we put dx always on the end. Okay, and we talked about what dx means, but just as a reminder, it's just telling you, hey, x is my variable. That's all it really means. And it has greater purpose than that later on, but for us right now, it's kind of like the ending part of a parenthesis saying, and x is my variable. So that's all this question is asking. So some of your questions inside a web assign don't go farther than they ask you to. Simply say, set it up. We can do that, right? You're just looking at the upper and lower limits of integration and the function that they give you. Now this one's a little bit different. This one actually starts with an equation. It tells you to sketch the region. So we're going to do that. And then it says to use a geometric formula to evaluate the integral. So there's not a whole lot of geometric formulas that you have that you're sort of ready at your disposal, but there are a few. So let's just chat real quick about some geometric formulas for area that you know really quickly. Tell me a formula for area of a specific shape, actually, that you know how to find the area of really easy. All right, so an area of a rectangle. You know how to find the area of a rectangle. It is length times width. Fantastic. What's another area that you know how to find real quickly? A sphere. Okay, so if you had, let's actually talk, not a sphere, but a circle, right, is what you really mean. So if we had the area of a circle, do you guys remember the area of a circle? Okay, yeah, so it's actually pi r squared, but we actually won't have circles. We will have half circles. Because if we had a whole circle, it wouldn't be a function, right? And so then it would be the 1/2 pi r squared. Okay, so those are shapes that we know. There's a couple others that I think you know too. you might not be thinking of right off the top of your head. Do you remember what that's the area of, Nick? Huh? It's not a trapezoid. Well, no, not a trapezoid. It's a triangle. Yeah, we're going to get to a trapezoid next, though. So the area of a triangle is 1/2. We'll call it base times height, like you said. You could also call it length times width, depending on how you're thinking about your image. But yeah. And then area of a trapezoid is another one that I wanted to mention, so I'm glad you brought it up.
I thought it was like side 1 times side 2.
Close. Yeah, this is one you don't see used quite as frequently, so it's one we don't always remember as well. So it is 1/2, like you mentioned before. And what you use is the two bases added, not multiplied, but added. I'm running out of space. Let me make this a little bit smaller. And then it's multiplied by the height. So what it actually does, just as a reminder, is this actually does the average height. It takes the tall height and the short height and it averages them. That's what happens when you add numbers together and divide by 2. So it's the average height divided by, or multiplied by the width, or vice versa, average width multiplied by the height. That's what's going on. So, I mean, this is really it. So when we're taking a look in this section and it's asking us questions about geometric formulas, it's going to look like one of these. It's going to. We just have to decide which one it is, okay? So let's take a look at this particular shape. The shape that it gives us, if I draw it, looks like what? What is the equation it gives me?
It's just a
Okay, it's just a line, and you're drawing it in the air without saying the words, and you mean horizontal, right?
It's just a rectangle.
Yeah, so it's a horizontal line at a height of 4, because this is a line y equal 4, and it goes from 0 out to 3. So this is the shape that I'm getting, and of course Jeffrey's exactly right, it's just a rectangle, right? So what is the area of this shape?
12.
It's 12. It's 4 times 3. 4 is the height, 3 is the width, so the area is 12. Okay, so when I ask questions about this on the test, always people want to do things so much harder. So I know I mentioned it on the last test. This is one of those places where highlighting the actual specific way it wants you to do something might be really valuable, underline, circle, whatever. If it says geometric formula, you need to use a geometric formula. You need to use the rectangle or the trapezoid or the whatever it is to make it work, okay? So this one happened to be just a rectangle. Let's see what's next. Oh, okay. This one, if you're not sure how to graph this one, please grab your calculator. But the same directions apply on this one. Sketch the region and then use a geometric formula. Okay, so geometric formula showing up in here again. It's got to be one of those. I think we listed really 4 different ones, but it kind of looked like 5 because we had the circle and the half circle there. What in the world is this shape look like when I draw it? Close. If I draw it far enough, yeah. What's the equation look like without shading anything? It's just a line, but this one's not horizontal, right? So is this one going to be increasing or is it a decreasing line? It's increasing because the slope's positive. So it crosses at 4, right? That's my y-intercept. And it has a slope of 3. So for every one we go over, we go up 3. So if I were to draw this shape, it looks something like this, roughly. Now, right now, it looks like there's a triangle on the left-hand side. It looks like you've got this infinite thing on the right-hand side. And the point is that you have to figure out where the shading goes to be able to figure out what your figure looks like. So this shows that my shading should go from 0 to 2, right? So here's my number 2 out here. It's somewhere like this. And if I shade between 0 and 2, I'm shading this right in here. So I've got a trapezoid on this one. Does that make sense? If it had continued all the way over here to wherever it was crossing, you would have a triangle on this one though, right? And you can definitely have the limits of integration go negative. There's no problem with that. We could have seen that happen. So that's why the shading is really important, just to identify that figure. So this is a trapezoid. So the area of a trapezoid that I wrote on the other screen says I need 1/2 base 1 plus base 2 times the height. Now the height is the constant piece, the piece that doesn't change. So in as much as this looks kind of funny, the height is actually what we would normally call the width in this case. It's right here. Does that make sense? That's actually the height. And so, yeah, it's 2. And here's my 1/2 at the beginning. The bases are the 2 pieces that are different. So in particular, we have one of the bases that's the y-intercept. So you actually know that one. It's 4. What is the other base? And how did you get that?
Add 6 to 4.
Okay, and in particular, you noticed it's got a slope of 3, so you added 3 twice, or maybe you looked at the original equation, you said, I'm just going to plug in 2, so I have 6 plus 4. Any of those kind of variations would work. But yeah, I have a height of 10 on the other one, so this gives me, when I multiply it all out, what? 14. So this area is 14. Okay, is that all right? So this is geometric formulas. All right, we have a definition next about how definite integrals can be manipulated or changed and equal other quantities. So if you take a look, this is 2 special definite integrals. It says if if f is defined at x equal a, then the antiderivative from a to a of f of x is 0. Now that should make sense. Because if you start and you end at the same spot on the graph, do you have any area? No, there's no width. So that one's pretty good. I mean, like you start and end at A, you're not going to have any area. There's no shaded region. The second one's a little bit more interesting. It actually tells you what happens when you change the order of the limits of integration. So if A is your top number and B is your bottom number, and you switch them, and then you do B is your top number and A is your bottom number, it just negates the quantity. It's kind of like what happens when you talk about absolute values, right? It's like 5 minus 3 and 3 minus 5 are the same thing, except their sign. Are you with me? So this is like that. So if I switch the limits of integration top to bottom, and sometimes it makes sense to do so, I just change my positive to my negative or my negative to the positive on the value of the function itself. There's a very nice property. This is called the additive interval property. And again, all of these kind of make sense. What this is saying is that if I have an interval that goes from A to B, and C is somewhere in between, right? And there's some shading going on above it. I don't care what it is, but it's shading in some region, whatever it is, okay? That what I could do, if for some reason it was helpful, let me make my shading a little smoother. I know it's yellow, but it doesn't really matter what the values are. What I could do, instead of calculating all that area at once, is I could break it into 2 pieces, and I could calculate this area 1 and this area 2, and I could add them together. That makes sense, right? I should be able to break it into 2 pieces. And why might that be helpful? Well, one of the things that we mentioned last time is that as long as you have a continuous function, it's differentiable, and that's true. But imagine that you had a continuous function that had this sort of a funny shape where it did this, and it stopped, and then it came over here, right? It was a piecewise defined function, and so you had this shape. We'll draw an open circle right here. Well, the first one had one equation, and then it changed equations. It's still, and I needed it to be continuous. I wanted it to touch, but not be the same equation. My bad, I drew it wrong. How about like that? Okay, they touch, they're continuous, but I can break it apart into 2 pieces, and I can still calculate the area because the number line itself from A to C to B always continuous, okay? And one more, Theorem 4.7. And I used this property last time. I told you we'd get there. I was thinking it was in the same lesson. I was wrong. But this actually talks about what happens when you have constant multipliers and addition and subtraction. And what I mentioned when we did it is everything like happens the way you would want it to. Right, so when there's a constant multiplier, I can pull that number out in front. It doesn't have to affect the value. If there's addition and subtraction, I can separate the integral, the antiderivative or the definite integral into 2 pieces with the addition and subtraction. Again, those are things we actually saw in 4.1, and then we used them in 4.2, and now we're seeing them defined yet again in a slightly different context for definite integrals in 4.3. All right, so you ready to try a couple of examples? Okay, so we're still not at the point where we're evaluating using the antiderivative process that we did in 4.1. We will do that in 4.4, so we'll get to that next time. But what they're wanting you to do is they're giving you some pieces of information. these three in particular. And they're wanting to use those three pieces of information to find this value of this kind of combination function. And what we're going to do in order to find that is we're going to break it apart into pieces that actually look exactly like one of the three pieces of information we already have. Okay? So we don't have pieces that look exactly like what we had, but you'll notice there are pieces that look similar. For example, this piece right here looks like that piece, right? The second one right here looks right, except it's got a 3 in front of it, so that's a little bit different. And the last one has an 8, but that doesn't seem to match quite anything. Okay, but we're definitely seeing that there's 3 pieces added and subtracted together, right? There's 3 separate pieces. So the first thing we're going to do is we're going to separate it into 3 separate integrals. So we're going to write integral from 2 to 4 of x cubed. And then we dx it, right? We close off the end of the antiderivative. And then I have, I'll do it right this way for now, plus from 2 to 4 of negative 3x dx. You could put the minus out there. We will in a minute anyway. Plus the integral from 2 to 4 of 8 dx. So all I've done right here is this step number 2 back here. I've separated everything with addition and or subtraction. The next thing that I want to do is, again, this first piece looks perfect. I have no problem with how it looks. It looks like exactly like one of the ones I have. What's wrong with the second one? That's the third one. There's a negative 3 though, right? There's a negative 3. So what does the property number 1 here say I can do with the negative 3? I can pull it out in front. So this first piece, I'll just rewrite for now. 2 to 4 of x cubed dx. If you want to evaluate it, you could, but I'll rewrite it for a moment. And then this says I can pull out the negative 3, and then I can write it from 2 to 4 dx of x dx. Okay? It's okay? That's the same thing. And then Kaylee mentioned there's this one that's got the 8 in front of it, right? Well, this is kind of like multiplication, really. There's an 8 here, and there's a dx here. So just like with the negative 3 that I was able to pull out in front, I'm also able to do the same thing with the 8. So it looks like I've got 8, and then the integral from 2 to 4 dx. And then it looks just like the last piece, too. Make sense? So we're applying these properties of integration, but we're not doing any like antiderivatives. All we're going to do now is we're going to use the values we were given. What does the integral from 2 to 4 of x cubed dx equal? It's 60. So I can simply replace this value with its equivalent numerical expression, which is 60. And then I still have the negative 3. What is the value of integral from 2 to 4 of x dx? That's 6. And then I have my plus my 8, and I can replace, what's the antiderivative from 2 to 4 of dx?
2.
It's 2. And then it's addition and subtraction. Okay? So if we add, subtract, multiply, and so forth, what do we get for our value on this one? 58 is correct. Does that make sense? You're breaking things apart. The next one's a little bit different. What do you notice on this that's different than the last one?
It's 2.
Ah, the limits of integration are in the reverse order. Do you see that? Oh, yes, I'm so sorry. You bet. You bet. Okay. So Kaylee said she noticed, and I think a couple others I heard echoing as well at the same time, that the 2 and the 4 are in reverse order, right? So what did it say I'm supposed to do if I have my numbers in reverse order? Whoops, I don't know where that went. Where was my property that said that? More. There it was. Awesome. So I can switch the order to be correct, or the same as what I had before, if I simply put a negative in front of the antiderivative itself. So that's what I'll do. The very first step is to pull this and make this a negative out here. And then I can go from 2 to 4 of x minus 7. Now, if you don't like the negative in front, you could actually multiply this negative through and make this negative x and positive 7 if you really want to. But it's just going to have to come back out. I mean, like, you know, it doesn't hurt anything if you did that. But it can also just stay in front. Now, again, part of this has addition and subtraction in there now, right? So just like on the previous problem, I need to separate this into 2 antiderivatives because there are 2 pieces separated with addition and subtraction. Now, the interesting thing in doing so is to remember that the negative that's in front will apply to both pieces. because it applies to the whole piece together. It will apply to each of the pieces separately as well. So I have the antiderivative of from 2 to 4 of x dx minus the antiderivative from 2 to 4 of negative 7 dx. Now, except for the negative, the other piece of this first one, the integral from 2 to 4 of x dx, that looks exactly like one of the pieces of information. This one doesn't quite yet. What do I need to do to get the second piece here to look right? Right, pull the negative 7 out in front. So my last step before I can actually put numbers in, if you will, we'll say x dx here. And then I'll have positive 7, because the negative pulls out with the negative that's already there, dx. Okay? These are actually incorrect or proper. They match. They match what I already have, right? So I have the negative in front, but what is the antiderivative from 2 to 4 of x dx? That's 60. No, 6, sorry. My screen was zoomed out, zoomed in, so I couldn't see. And then I have plus 7, and then what's the antiderivative from 2 to 4 of dx? It's 2. And then what's negative 6 plus 7 times 2? It's 8. Okay? So the reality is, this whole section, aside from the separation of things and so forth, it's really just a lot of arithmetic. Right? Basic geometry formulas and arithmetic. That's what you're seeing happen in 4.3. Okay? So over the weekend, you should be preparing. Obviously you need to do this homework. It's assigned. But you should also be preparing for your antiderivative gateway, which is on Monday in class. Okay?